Hello, and welcome to Physics for Play. In this episode, we are going to be continuing our discussion of the damped harmonic oscillator and looking at how to use the Mathematica command DSolve to get solutions for it. Let's get started. All right, we're going to continue our discussion of how to solve the damped harmonic oscillator. If you recall, in the last video, we set up our equation for the drag force. We plugged that into our differential equation for the simple harmonic oscillator. We didn't go through the full solution. We left that as a home exercise, but we wrote down the solution. We animated it. We made some plots to show what that looks like. And now we're going to show how to actually solve that differential equation, this time using the Mathematica function DSolve for a differential equation solver. So to begin, what we are going to do is we are going to take our differential equation that we wrote down last time, and we're just going to plug it into DSolve and get our solution. In this case, we do need to still specify we want to solve for x, and we want to make sure it knows that x is a function of t. Before beginning, I see I've still got some x's defined, so I'm going to quit my kernel, which will turn those x's blue so that they're undefined. So we start with a nice clean kernel. And if I run this, you'll see we get x, which is a function that looks like this. We've got a couple of constants that need to be specified by the initial conditions. It's two constants since it's a second order differential equation. We can also we can compare this to the solution we showed before, and you can see it has a very different form. I will not go through the algebra here other than to say you can see that these are exponentials. You can see this is a cosine function. If you were to go through and look at these constants, see which ones were positive and which were negative, especially in this square root. If you have a negative inside the square root, that's going to get you imaginary numbers. And once you have an imaginary number in the exponent, that gets transformed into sines and cosines. So I won't go through the algebra on that. I will just say that this is the correct solution, and you can show that these two solutions are identical, aside from some algebraic constants, which are, you can work out the algebra to see how those are related to each other. So once we have our solution, we could go from there, but I'm actually going to go a little bit further, and we're going to solve this with initial conditions now. And with initial conditions, I'm going to put in several equations. So we've got our force equation. We've got our equation of motion there. I'm going to put in an initial value for my position. So that's going to be x at time t equals 0. And we're going to say our initial value, our initial position is 1. And we'll give an initial velocity of 0. You can change these up if you want. If you want to give it some initial velocity, you can put in some number for 0 here. But recall that x prime of t is the velocity. And if I run this, you can see we get quite a bit more complicated of an equation. It's the same thing we have before. The main difference is rather than having this C1 and C2 constants, it's plugged in for the initial conditions, so it looks a little bit more complicated. We are actually going to plug numbers in here to make this a little bit simpler. So I'm going to give the spring a stiffness value of 1. I'm going to give the mass a value of 1. What else do I have to plug in? I'm going to plug in a damping constant, which I will we'll make that a little bit smaller. I'll make that 0.5. And if we run this, you can see we get a nice equation that now only depends on time. We can go ahead and plot that equation. I think I did up here. I am going to copy, because I'm lazy, I'm just going to copy and paste the plot function we already made earlier. for the original solution. Now I got to do a few things. So x of t is not defined. You can tell that because the variable is blue. So I am going to define my solution here to be this function x, which I can replace the x of t in here with that solution. And we should be able to get a graph nice and easy with that. I'm going to crank up some numbers here to make this a little bit different. Let's give it an initial displacement of 7. That way we can see it a little bit better. Let's see, I'm going to change my label just to be a little bit bigger so we can see that better. Make that 20, and now my graph is too small, so I'll just increase the image size. There we go. So we can see how our displacement changes as a function of time. Now, what's fun is once I have this plot for position as a function of time, it's very easy to get plots of other functions. So I'm just going to copy and paste this. Copy and paste that whole thing. If I run it again, I get the same plot. It's just position as a function of time. But all I have to do is change this to the velocity, x prime. I should probably also change my axis label to be velocity rather than position. We'll make that velocity in meters per second. And you can see you get a plot of the velocity. Now, is this correct? Let's see. Well, we started with an initial velocity of 0. We can see my initial velocity here starts at 0. Then it becomes negative, which you can tell it's a negative velocity because here we start at 7, a position of 7, and then the position gets smaller, so it's got to be a negative velocity. And if you match this up, you can see here the position has no slope, so I should get no velocity there, and velocity is 0 at this point. So you can match it up very nicely there. Everything works out hunky-dory, and all I had to do was copy and paste my graph and put an x prime in there. Up next, I'm going to make another plot of my solution. Let's see what happens if we plot the energy. So the energy is going to look a bit different. And actually, I'm going to plot a few different energies here. So we'll do the kinetic energy first. That's 1/2 the mass times the velocity squared. We can plot the spring potential energy, which will be 1/2 k times x of t squared. And we can do the total energy, which is 1/2 mv squared, the kinetic energy, plus the potential energy, 1/2 kx squared. Now, I think I'm going to try this, but I think if I plug in, it's going to get confused. Oops. Let's make sure we plot the full range of this. Yeah, it's getting a little bit confused here. I'm going to wrap this whole thing in an evaluate function, which should separate out the different terms here. Yeah, that looks quite a bit nicer. I'm gonna give the plot range, gonna make the plot range go to all. And here we can see, we also want to plot legends in here. So my first term was the kinetic energy. My second term was the potential energy. My third term was the total energy. And if we plug in, now we've got a nice labeled graph. I know exactly what everything is. And you can see this is interesting because you can start to see what happens to the total energy as a function of time. So it's clearly decaying, but it's not decaying at an equal rate at all times. You can see where you're getting the biggest drop in kinetic energy when you have you get the biggest drop in the total energy when the kinetic energy is largest. And that makes sense. If I look at where am I losing energy, it's my drag term has a velocity in it. So I'm obviously going to lose more energy when it's moving than if it's not moving. We can also check to make sure that this is conserving energy, which it should do if this is just a quick sanity check. If I set my damping constant to 0, I should conserve energy, and you can see my displacement doesn't appear to be losing any amplitude. My velocity doesn't appear to be losing any amplitude. And you can see my total energy is constant. It just switches back and forth between kinetic and potential energy. So we'll go back one more time, and just to make this look like it's a damped harmonic oscillator, we'll run through this one more time. And we can see that energy start to drop. We can, let's see, I want to do one more plot here because we talked before about doing phase diagrams, and it's easy enough to do a phase diagram. I'm gonna start once again by stealing this plot from up top, so I don't have to copy all the graphic styling options that I have here. But I'm going to change this not to a plot, but to a parametric plot. We've done one of these once before, and I am going to plot x of t versus the velocity x prime of t. And we're going to do that from t goes from 0 to 10. And let's see, I need to change my x-axis is now no longer time. It's going to be displacement, which is going to be in meters. And I think this should work. There we go. So you can see what's going on here. We start off at no velocity at this point right here, and with a displacement of 7, of x equals 7. And then we start to get some negative velocity, so we go into the negative half, the bottom half of the chart. So we get negative velocity here. As we get more negative velocity, x gets smaller and smaller and smaller. X starts to become negative, but the velocity starts slowing down until velocity becomes positive. When velocity becomes positive, x starts increasing. And you can see if I animate this for a large, or if I plot this for a large enough time, you can see the displacement and the velocity starts to spiral into the center. These phase plots can be interesting to look at. They can give you some nice, interesting physics that shows up there. So they can be fun to play around with as well. Now, if we want to animate the solution, that's the solution that we got from DSolve. That's easy enough to do. So we already built up, I'm going to scroll up here. We already actually built an animation when we wrote down our x of t solution before. So I'm just going to copy that solution. Copy that, minimize this, minimize that. And I'm going to just drop the whole thing in there. Now, you'll notice my x of t is blue because I haven't actually defined what x of t is. When we did DSolve and we solved for that, we didn't actually say x equals anything. We said there is a solution that you get where x becomes this function. But that solution was stored in a variable called SOLN for solution. So I need to replace these x of t's with that solution. And I could copy and paste the solution, but I am actually going to use Mathematica's replace all function, which is / solution. And I can do the same thing down over here. We'll plug that in. I'm going to plug a / solution anytime you see an x of t, and that will replace those x of t's with the solution from the differential equation. And when we do that, I believe This should work. There we go. Very nice. And I just plug it in, and you see you've got the animation that you had before. This time the solution came from DSolve, so we didn't have to do any real effort aside from plugging the values in and just looking at the solution, because Mathematica is your friend. That's all we're going to cover this time. So please check in next time, where we'll start to explore a little bit about the physics of what happens with damped oscillators, where we'll look at different damping cases of being overdamped, underdamped, and critically damped. Like the video if you liked it, and if you'd like to see more, please click subscribe.